Hello, in this video we're going to look at subspaces, and we've talked a little bit about subspaces before, and we're going to practice a few more examples in that area. So recall that a subspace W of a vector space V is a subspace of V such that for all vectors U and V in W, U plus V is in W, and this is what's known as the closure under addition property. So we've got closure under addition. And the second property is a closure under scalar multiplication. This says for all vectors U, and again this is in W, and scalars, and again these scalars are real scalars for us, C times U, that scalar multiplication, that is in W. So this is what's referred to as closure under scalar multiplication. And so the picture here is, we have a big set, V, and then we have some other set, call it W. W is a subset of V, so we say W is a subset of V. And that notation's not important at the moment because we're interested in the concepts. This is not a proof-based linear algebra course. But anyways, that subset of W, we want to know if we pick things in there, like a U, vector U, and we pick some other vector V, where does the sum, where does U plus V live? If U plus V lives out here, if we fall outside of set W, then that's not closed under addition, right? That would be bad. So we would want to see if the sum U plus V lives in W. So that would satisfy closure under addition. And then again, we're picking scalars, C, those come from the field of real numbers, and the question is, does C times U fall outside of W, or does C times U live inside of W, which is what we mean by closure under scalar multiplication. Okay, so let's look at an example. Let's let W be the set of vectors which are of the form A plus 2, where A is a real number. And W is certainly a subset of R3. We know that because there's 3 components to the vectors in W. So let's check for closure. So let's check for closure under addition. So if we check for closure under addition, the first thing we need to do is we need to pick, and I'll put this in another color, let's pick 2 vectors, U and V, in W. And so if we have some vectors living in W here, it must mean that U is of this form. That's the defining feature of living in W. So U must look like A plus 2, and V must look like B plus 2, where A and B are real numbers. So the question is, what happens when we add up U plus V? Do we stay in W or do we fall outside of W? And so if we add these up, we get an A plus B, an A plus B, and an A plus B plus 4. And this does not follow the form for W. Recall that W said, hey, to live in W, you need vectors of the form anything in the first spot, anything that matches that in the second component, and then that third component, you still need that same creature, that same number, but you're going to add 2 to it. And so the entries in those components have to follow that form, where the first 2 are equal, and the third one is greater by 2. And that's not what we have, right? We have same thing, but this third component is a +4. It's not a +2, so that ruins it for us. So we would say, in this case, W is not a subspace. So that's our answer for this one. Let's look at another problem. In this problem, we're looking at the set of vectors. So let's let W be the set of vectors in R3. We've got 3 components, and these look like x, y, and 0, where x and y are any real numbers. And this is a nice example because if we look at the 3D coordinate system, we're really just looking at vectors x, y, 0. We're looking at vectors that live down here in this x, y plane. So we're looking at anybody that lives down here in this plane. And we might suspect that that is a vector space or a subspace of R3, but let's go through and verify it. So first property to check is closure under addition. So let's pick 2 vectors in W, and to live in W, you can have anything you want in the first component, anything you want in the second component. The third component has to be 0. And now picking another vector, let's call it AB0, and we'll specify that this x, y, a, and b, these are all real numbers. They're not bananas or something silly. And then we add them up, we get u plus v, and that is a x plus a y plus b, and a 0. And that does fit the form of living in W. W said you can have anything in the first 2 components, but the third one has to be 0. And we've met that condition here. Next, let's check closure under scalar multiplication. So to do this, let's pick any c in the real numbers. And of course our u still looks like x, y, 0, where x, y are elements of the real numbers. And we multiply scalar multiplication c times u, and we're going to get a c times x, a c times y, and c times 0 is 0. So again, this fits the form of being in W. And since we satisfy both of those properties, we can conclude that W is a subspace.